Okay, so let's get started with our morning session. So we will continue now with the second lecture from Leon.
Thanks, Mike. Okay, so last time I kind of obsessed a lot about the toric code as a simple model of highly entangled, what I called ultra-quantum phase. It's also a topological phase, so you've heard lots about topological phases. So today I want to really talk about quantum spin liquids that go beyond topological phases. So just to preview, so the plan is today I'm really going to be focusing on some sense of more theoretical side of quantum spin liquids. I'm going to talk about models and different possible phases that would be considered quantum spin liquids. And then tomorrow the plan is to talk about experiments. Okay. So what I want to do is start by going through another kind of simple example, which we actually heard a little bit about yesterday, which I think is a nice one, which is these days goes by the name of quantum spin ice. So this is nice because it's quite different. Has some conceptual similarities with this toric code spin liquid, but it's different. It's not topological. It's what we call, it's not two-dimensional, but three-dimensional. It's what's called a three-dimensional U1 spin liquid state. It has, with a little bit of modification, quite a bit of experimental relevance. And it's one of the simplest examples of non-topological ultra-quantum matter. And I'll go through that example, and then, like the toric code, this is really based on a particular model, which happens to be simple enough that we can make a lot of progress with it without making really very many approximations, and understand it more or less completely by a combination of analytics and numerical studies. Most problems in quantum spin liquids are not like that. We can only get to a couple of simple examples of phases in this way. So the rest of today I will, after doing that, I want to talk about some of the more popular general methods, which are rather less controlled than this, but which you'd encounter all over the place if you're trying to read some of the literature. And in particular, I want to talk about partons and constructing more spin liquids. Okay, so that's the plan. So let me start with this quantum spin ice story. Okay, so yeah. Yeah, I'm not planning to, just for lack of time, but go ahead. Yeah, okay, so maybe the prequel to your question is what is a spin liquid? I didn't define it, and I'm not so much wanting to define it, but one kind of nice definition is it's a state which has non-local excitations. Okay. Now that begs me to define non-local excitations. It gets a little bit tricky, but still something identifiably non-local like that. Okay. Another kind of more theoretical definition would be that it's something which requires using some kind of emergent degrees of freedom to describe it. It's another way. Well, so historically, that's what people called quantum spin liquids. They would be states of spins that are paramagnetic. And and I'll mention a little bit about the history, but it turned out, that the first quantum spin liquid state that was really proposed, it was just a wave function proposed by Anderson back in the 70s. Not only was paramagnetic, but it also had these kind of non-local properties to it. It was a very highly entangled state. Okay. These days we think the high entanglement is much more interesting. The paramagnetism is not all that interesting and not even essential. So we could have states that have the same kind of complex entanglement, which have support non-local excitations like that, but actually have some magnetic order. Okay. So that's why I'm not so much focusing on that. But the textbook, I don't know if it's probably not really in textbooks, but traditional definition of spin liquid is it's a paramagnetic ground state of a quantum spin system. Yeah. Well, yeah, so I'd rather do it by example, but so most of those attributes are particular to topological phases. Okay. In just about all other examples, we can't even necessarily all that well define the notion of ground state degeneracy. Okay. A real system never has exact ground state degeneracy. It has some maybe asymptotic degeneracy in the sense that certain levels approach the energy of the ground state much more rapidly than other levels. That really only happens when you have a gapped system. So a fully gapped spin liquid would be, at least by my definition, that will be a topological phase. Okay. But anything which is another one of these quantum spin liquids which is not topological will not be gapped. Okay. And as a consequence, the scaling of low energy levels to each other, if it happens at all, is going to be much slower than it would be in a fully gapped system. Okay. So then the answer depends very much on the model, on the particular phase rather than model. There's still universal questions like that. Generally, I'll comment on it in this specific example, this notion of indistinguishability, and that something is really, you have a non-local excitation which cannot be seen from far away without some global measurement. That's a sort of a property of a topological phase. If I have like in the toric code, if I have an E particle somewhere, any local measurement somewhere else far from it cannot tell that particle is there. The only way to tell is by doing some measurement over a region which actually encircles the particle. Okay. And that's not true for other spin liquids. You can have non-local excitations, which, however, can be detected by a local measurement from far away. That'll be the case in this example. Okay. So there are lots of differences, all right? Many things you learn about topological phases don't generalize. Okay. Topological phases are just very, very simple. Okay, maybe don't seem that simple after you've heard about, modular tensor categories and representations of the braid group and topological quantum field theories. Okay. The only reason it's so complicated is because you try to understand every topological phase. If you just wanted to try to understand one, you wouldn't need all that machinery. Okay. All right. And it's only because topological phases are so simple. Do you have any hope of understanding every topological phase? Okay. And even there, they're not simple enough. In 3 dimensions, it's already hopeless at this point, probably. But I don't know. I'm not qualified to address that. Maybe Shi-Chen, I don't know if she's here yet. Comment, or Mike or somebody. Okay. But like I said, I want to orthogonalize myself to the rest of the speakers now by not talking about topological phases. Okay. More questions? Questions are good. It's probably more interesting than the actual lecture. Okay. So let me tell you about quantum spin ice. Actually, this started really as some work that we didn't know about quantum spin ice, some work that Mike Hermele did in the early part of his thesis. Where's Mike? There, he's hiding back there. Early part of his thesis with Matthew Fisher and myself. We were just trying to find models for exotic phases, so we looked at a very simple model. It's really just an XXZ model. Let me write Hamiltonian. So we have a Z coupling, which for some reason we started calling JZZ, between nearest neighbor spins. These are spin 1/2 spins. Oops. It's nice chalk, but a little bit soft. Okay, so this is, this model is kind of one of the most well-studied models of magnetism ever. Okay, you can put this on many lattices. I've chosen some signs here. So I've chosen antiferromagnetism for the Z component of spins, just because that makes this kind of, if we work in the Z basis, this is the classical part of the Hamiltonian, makes it non-trivial. And then I've chosen ferromagnetic XY coupling. It's not so important, but it simplifies things a little bit. Okay. So we can, one way to view this is that this is a classical Hamiltonian. If we turn J plus minus off, SIZ is a constant of the motion, so it's just an Ising model of some type, and this induces quantum fluctuations. Okay. Of course, if we took J plus minus negative so that this thing was positive, there'd be a value of J plus minus, which is, I don't know, a half or 2 JZZ, and remember how it works, where this becomes a Heisenberg model. Okay. Lattice is important, so we're going to put this thing on a lattice that makes it interesting, particularly interesting, which is the Pyrochlore lattice that Roger mentioned yesterday. It's hard to draw, but it's a lattice. You can embed it, the whole thing, in a kind of large cubic unit cell. It's a lattice of corner-sharing tetrahedra. It looks something like this. If I only draw 2 tetrahedra, I'm fine. Once you get beyond 2, it becomes hard. So you can all Google it and find lots of pictures of this thing. Okay. It's not really that complicated. It looks kind of complicated, but it's one of these tetrahedra would be a unit cell. There are 4 spins in a unit cell, and you can build the whole thing up by this. It has basically cubic symmetry, and it's not all that complicated. For our purposes here, what's important is that it's, from the point of view of an Ising model, it's very highly frustrated. So that with this JZZ positive, I'm going to define all these things positive. This Ising interaction between spins is highly frustrated. It's got lots of triangles in it, so we can't anti-align every pair of spins. So the best we could do, so let's turn off J plus minus and just understand this kind of classical limit. The best we could do is, we try to minimize this term, and we can write H then as JZZ over 2, sum on these tetrahedra. So in every unit cell, that includes 2 tetrahedra, one up one if you want, one down. So they form a sublattice like this. It could be called a tetrahedra, and this is a B tetrahedra. This would be then connected to another 3 A tetrahedras over here. Okay. And then on every tetrahedra, I write the sum of the spins on that tetrahedra, SIZ squared minus a constant. Okay, so if I multiply out, there are really 4 spins here. It's 1, 2, 3, 4. Square this out, I get a bunch of constants. SZ squared is just a quarter, and then twice SIZ SJZ for all these bonds. Okay, so that's what's nice about these tetrahedra. A tetrahedra, is just a fully connected graph of 4 sites. Okay. Okay, so from this representation, it's obvious that the best you could do is to make this sum 0 everywhere. Okay. So any state in which the four z components of the spin sum to 0 is a classical ground state at j plus minus equals 0. Okay. So there are many such states. There's many ground states. In fact, there's an exponentially large number of them. The entropy, so that the number of ground states, scales like some entropy times the number of spins or the number of unit cells. Okay. It's exponentially large. And every such state has 2 up spins and 2 down spins on every tetrahedron. So that's the way to get it to add to 0. Right? A half plus a half minus a half minus a half is 0. Okay. And now, so that's a classical model. It's kind of very simple classical model. Has a lot of degeneracy. At 0 temperature, we don't know what the ground state is because there are just too many of them. But we expect that that degeneracy will be broken somehow if we include j plus minus. So what about quantum spin ice? Why do we call it that? I don't want to go too much into this, but there's a whole set of materials, real materials, which have this pyrochlore lattice structure. It's very common. It's one of, second or third most common mineral structures on the planet. Lots and lots of materials with the structure. Lots and lots of them have magnetic moments, have spins on the sites of this lattice. The most well-studied ones are ones where you have rare earth spins here. Rare earth spins have a lot of attributes that make them sometimes complicated, sometimes very simple. In these compounds, most of these rare earth pyrochlores, you can think of these spins as having only 2 important low energy states. They have a ground state doublet. And the doublet has a kind of physical interpretation. The up and down levels of that doublet have the interpretation of a spin pointing one direction or the other along this local axis of symmetry. So you imagine these 2 tetrahedra are attached. There's a 3-fold symmetry axis here. Okay. And many of these systems, not all of them, have this kind of interaction, this kind of effectively antiferromagnetic interaction. And so these 2 up, 2 down states in these spin ice materials are usually referred to as 2 in, 2 out states. Because the local Ising axis is actually some along these symmetric crystalline axes. Okay. So this is often referred to as 2 in, 2 out. Okay. All right, so that's a setting. I won't talk really any more about these materials right now, maybe tomorrow. Good. Okay, so now let's think about doing perturbation theory. Bless you. I couldn't see who it was. Okay, so we're perturbing around this classical model, and it's degenerate. So this is degenerate perturbation theory. It's very highly degenerate perturbation theory, right? So the rules of degenerate perturbation theory is that to first order, you should take the perturbing Hamiltonian and diagonalize it in the degenerate subspace. So there's some effective Hamiltonian, which is a projection into the ground state subspace of the perturbing Hamiltonian, call it H plus minus. That's usually what you learn in undergraduate quantum mechanics. Unfortunately, this is 0 because the ground state subspace is exactly that subspace where the total spin on every tetrahedron is 0. And you can see if I act with S plus S minus on any bond, let's say these 2 sites, I and J, I act with plus here and minus here. it doesn't change the spin of this tetrahedron, but it will change the spin of this one. Okay, it'll raise the spin of this tetrahedron from 0 to 1, and so now I'm out of the ground state subspace. Right. So this is just 0. But, okay, maybe in graduate quantum mechanics or good undergraduate quantum mechanics, you'll learn that there's then a correction to this, which is second order, something like this. I don't trust the sign here. We need kind of 1 minus p ground state here. Okay, so this is the next term in degenerate perturbation theory, second order in H plus minus. You can convince yourself that this, it's not 0, but it's a constant. Okay, so you get a non-zero contribution if you act on the same bond twice. You can raise one spin, lower it, and then raise it again, and lower the one you raised and raise the one that came back. But this actually gives a constant. It's just a constant. So this doesn't split any degeneracy. It's not so obvious, okay? You have to think it through. And then you get to the next term, which is, okay, more of this stuff. It looks like this, H plus minus. There's some operator here, H plus minus. Some operator here, H plus minus, P, where this operator is called the resolvent. It's basically this thing. Okay, that's the next term. Okay. And this term, you finally can actually get a term which is not a constant. Okay. And what is that? Let me just write it down and then explain it. We get that the constant it's actually a sum over hexagons of put a minus here. Okay, where I label the sites around hexagons like this. So discovering that there are hexagons in the Pyrochlore lattice, okay, that requires more than my drawing skills are capable of. But if you were actually able to extend this picture, you would find that there are loops in this Pyrochlore lattice that look like this, and they're kind of tetrahedra coming off of all these things. One way to, actually, if I just draw this picture, this is not a bad picture. This looks like a piece of the Kagame lattice. And now I can add a site to it above here and below the plane here. And they're sort of all connected. Okay, a little piece of the Pyrochlore lattice looks like this. So these are sort of the smallest non-trivial loops in the Pyrochlore lattice. They have these hexagonal form. Okay. With a little thought, you can sort of see why this is the right kind of term. Imagine we act with S plus S minus on one bond. So we already see this takes you out of the ground state subspace, because it raises the gives you a positive spin on this tetrahedra and a negative spin on this tetrahedra. So we need to act again with S plus S minus to try and bring back to the ground state subspace. So the trivial thing is to act again on this bond, but that doesn't really help us. So we'd like to kind of remove the plus sign here. So we can do that by acting with S minus, S plus, let's say on this bond. So that will zero out this tetrahedra and zero out this one, but now I've moved my plus sign over here. That's why at second order you again can't get a non-trivial term in this space. But at third order now I can act with minus plus here, which will actually fix these two extra charges. Okay, so that's how this comes about, and then by some combinatorics you can figure out what this prefactor is. let me call it K. And you find that K is something which I don't remember, but it's J plus minus cubed over JZZ squared. I vaguely want to say it's 12, but I'm not sure it's correct. But maybe Lucille knows what it is. Mike might remember. Doubtful. It's in his age, far past. Okay, there's some number. Not to be trusted. Number. Huh? It's 12. Okay, see? All right. Okay, so this is what degenerate perturbation theory tells us. The first non-trivial term describing now the splitting of this classically degenerate manifold is this. Okay, so that here's a new model. Looks a bit more complicated than the original model, but it has a lot of nice properties that one can try to solve. Okay. Unlike the original model, this has no dimensionless parameters in it, okay? There's just one coupling constant with an overall scale k. So the ground state of this model doesn't depend on k, it just depends on the sign of k. Okay. And actually the sign of k can be removed by some transformation, so it doesn't really matter. So we'll take k positive. Okay. It's a kind of weird looking model, involves this product of many spins. So one can kind of understand it a bit better, try to understand why we had to get this structure. Okay. So this structure actually follows really from the structure of the ground state subspace. This kind of, it really came from the fact that in the classical subspace, we had a sum of S equals 0 on every tetrahedron. Okay. The effective Hamiltonian has to satisfy this constraint. So this is a local constraint. So there are an infinite number of these constraints, one for every tetrahedron. In our effective Hamiltonian, this constraint, because it's satisfied, is going to commute with H. Okay. So we can define a quantity on every tetrahedra, which is this sum. And this operator has got to commute with H effective. Okay. Anytime we have a commuting operator in quantum mechanics, it generates a symmetry. So we can think about a symmetry operation, which is e to the I, let me call it chi qt. Okay. Or chi is a free parameter, so q is a real variable. It's a Hermitian operator, and so chi can be taken to be some arbitrary phase here. So this is a unitary operator which generates a certain symmetry, and what symmetry does it generate? Well, this is e to the I chi t, sum on I, remember I and t of SIZ. So it generates phase rotations of these of the 4 spins on that tetrahedron. Okay. So if we have I on t, this sends Si plus to Si plus e to the I chi. Might send it e to the minus I chi, I don't know. I never get this right. Okay. And it sends Si minus to e to the minus I chi t. Okay. That's, everybody understands that? Silence. Trivial. Okay, good. Okay, and these phase shifts have to cancel out in this way. So this is a local symmetry. So we would often call this a gauge symmetry. And indeed, it's a U1 gauge symmetry. So we should expect that our effective Hamiltonian should be some type of U1 gauge theory. Pretty much guaranteed. So to understand a little bit better how that works, it's helpful to take advantage of some specific properties of the geometry of this lattice, which I already alluded to, which is that hard to draw like this. That there are every spin here, I, is shared by two tetrahedra. It's shared by a tetrahedra here of type A, let's call it tetrahedra T, and type B, called tetrahedra T prime. Okay. So we can choose to view the spins very much like they were for the toric code as lying on the links of some other lattice, which connects the centers of these tetrahedra. Okay, we saw that was really useful in the toric code. It's useful here too. So we can associate every site with a link between two tetrahedra. And if we want, those two tetrahedra, I also mentioned the tetrahedra form two sublattices, kind of up and down. So this would be an A sublattice. This would be a B, an A, a B, an A, a B. So we say the lattice of tetrahedra is bipartite. So it means one of these tetrahedra will always be type A and one will be type B. Okay. So we can choose to label these spins as lying on a bond TT prime. Okay. So to kind of bring out this gauge theory picture, we kind of want to define things like their gauge fields. So to, usual gauge theory, the one you're familiar with is electromagnetism. We have electric fields, magnetic fields. They're all vectors, vector potential. So they have a directionality. If we measure along the opposite axis, they have the opposite sign. So it's kind of natural to define this SZTT prime to be equal to I if T is on the A sublattice and T prime is on the B sublattice. And we define minus this thing to be, if we, for some reason, choose the opposite ordering, T prime T, so this is a B sublattice tetrahedra and this is an A, then this is minus SZ TT prime. Okay, we can give this ordering to these links. We can assign an order to the links consistently. Okay. Good. And then similarly, we can define SI plus to be ST prime plus if T is on the A sublattice and T prime is on the B sublattice, and to be, this is where it's a little bit funny, S minus T prime T. If T prime is on the B sublattice. Okay. Does it make sense? So if we do that, this term becomes actually kind of simple. You look at our hexagon here. We can think about the label. We had our sites I, J, K, L, M, N. You can label these tetrahedra, I don't know, A, B, C, D, E, F. This spin is shared by these two tetrahedra. I should use another color here. It looks indistinguishable from the first one. Okay. If we draw the lattice connecting the centers of tetrahedra, it's the blue one. And so and now we remember that let's choose A to be an A tetrahedra. Then this B is a B tetrahedra. This is now an A tetrahedra, B, A, and B. So SI plus is S AB plus. Sj plus is actually SBC. So Sj minus is actually SBC plus, okay, because we have the opposite orientation of tetrahedra here. All right. Sk plus is SCD plus. Okay, you can see the pattern. SDE plus, SEF plus. It's 5, SFA plus. Okay. So by this notation, we achieve something very simple, that all the S's are plus. Okay. Okay, so equivalently, we can write our H effective as minus K sum over hexagons, SAB plus, SBC plus, etc. Okay. So you can see that this is actually kind of something simple. This is you're really just taking a product going around this hexagonal loop of these bond variables. Now also, with this notation, it becomes also kind of simpler to understand how these transform. If we go back to the U1 symmetry, the U1 gauge symmetry, so we can consider a general gauge transformation, which is a product of these. So e to the I sum on t, chi t, qt. And under this kind of transformation, we get that S plus t t prime goes to e to the I chi t minus chi t prime S plus t t prime. This is if t is on the A sublattice. Maybe this is general. Yeah. All right. So this is, now with this, it's very easy to see why this is invariant, okay? Because every index here appears twice, once on the right and once on the left. So this factor from the right-hand term will cancel with this factor from the left-hand term. Okay. So actually, this is just a slightly hidden version of something that is more familiar from gauge theory. And it's kind of helpful to bring that out. All right. So yeah, so to bring that out, I want to try and massage this Hamiltonian to make it really look like the gauge theory you're familiar with, which has electric fields and magnetic fields in it. So what should correspond to what? So, well, first of all, we know that conservation law is this QT. So QT appears like the charge, right? Oh, so now imagine you do this. So that's one gauge transformation. I choose to make a gauge transformation at the particular point t. But I can combine it, do as many as I want, and I just have independent parameters for each t. Okay, so this is just the product of many. It's slightly more compact way of showing it. So this is like what you do in electromagnetism, where you transform, the the wave function by some phase chi of r, right? And then the vector potential transforms by a gradient. Okay, so this is kind of similar to that. Right. So Q is going to take the role of the charge. And we know from electromagnetism that there's a Maxwell equation that the charge is a divergence of an electric field. So we should expect that S here is playing the role of an electric field. So in our new variables, we can think, well, all these spins they're shared by tetrahedron T and some other tetrahedron T prime. So this is just a sum over tetrahedron T prime, ST T prime Z. Okay. There's a little bit of a subtlety, small subtlety here, which is that, remember I told you this is equal to this only if T is an A tetrahedron. Otherwise, it should equal minus this. So we should put some sign here, some epsilon T, where epsilon T is +1 if on the A sublattice and -1 on the B sublattice. Okay. So this is like the lattice divergence. So we could basically define this to be the divergence of some electric field at the site T. Okay. So this suggests we should define an electric field E T prime, which is SZ T T prime. Okay. Okay. Now, because we're talking about a spin 1/2 system, this thing is only taking eigenvalues plus minus a half. So that's a little bit inconvenient. So we could, but we can always kind of get around that, make something that's a little bit simpler, and that turns out to be helpful, at least conceptually, which is to embed this in a set of eigenvalues, a set of states where ET can be any, not only plus or minus a half, but plus or minus 3/2, plus or minus 5/2, etc. So it's all the full set of integers plus a half. Okay. So this kind of variable where you have eigenvalues separated by integers, this is called a rotor. That's a very familiar example of something like this in quantum mechanics, which is just the eigenvalues of one component of angular momentum, like Lz. Okay. For a particle in the plane, it has eigenvalues, integers. Okay. And if you apply some anti-periodic boundary conditions, you can change that from integers to half integers like this. Okay. So if we work in this space of half integer eigenvalues, we can define a conjugate variable. If E is like the angular momentum, the conjugate variable is like the angle. Okay, so we can define a conjugate variable A such that commutator of A and T is I. Okay, maybe it should be minus I. I never get that right. Yeah. I have. I'm not. So I'll have to tell you how to fix it. Okay. It does eventually lead to understanding, but nothing is going to actually simplify that model. The model is what it is. It's the same as what it was over there when I wrote it S plus, S minus, just giving us a way to think about it and try to connect to something that's a little more familiar. Okay. But at the end of the day, one has to somehow solve this model and compare it to some theoretical expectations to understand what the low energy physics of this model is. Okay. No getting out of it. Okay. But this is a way to motivate that. Okay. So there is a limit, a rigorous limit of what I'm about to do, which will reduce it to that. Okay. But then we'll move away from the rigor. All right. So we can consider, this is kind of a standard way to have what are called rotor variables. You might have seen it in the context of, for example, a quantum dot, where you can talk about the charge and the phase of a superconducting quantum grain, where you have a number and a phase variable whose commutator is I. The kind of similar thing is going on here. E is taking the role of a number variable. It has discrete spectrum, whereas A is taking the role of a periodic variable. Okay. If we do this, then an operator like e to the I A becomes a raising or a lowering operator for E. Okay. So if we take something like e to the I A times E times e to the minus IA, this is going to be, on one particular bond, this will be E plus or minus 1. Okay. And that should be sort of familiar because this is just like position and momentum. If you, to get a translation of the E coordinate, we conjugate by the momentum operator. Okay. So you can convince yourself that if I write S t prime plus equals e to the I A t t prime, I probably need an epsilon here. This reproduces the correct matrix elements between the physical states with SZ equals plus or minus a half. Okay. So if I consider the matrix formed by SZ equals plus a half, SZ equals minus a half, this operator A, SZ equals plus a half, SZ equals minus a half, this is the same as the Pauli matrix or S plus matrix. Okay. It has other matrix elements, however, between other states. Okay, that's where the wrongness is. So long as we can force the Hamiltonian into just this subspace of the physical states, force the wave function into these states, then we won't make any error by writing this. Okay, so that's the way to do this. We can make the substitution here and this substitution here, but we need to add something to the Hamiltonian to force SZ to have eigenvalues only plus or minus a half. So to do that, what we do is we add some term here, sum on tt prime, e tt prime squared minus a quarter. Okay, so if e is equal to plus or minus a half, this is 0, and anything else, it's positive. And now we should really take the limit of u to infinity. We add this to h effective. I'm going to erase this, which now looks like minus k projection sum on hexagons. Now we can just plug in this formula for S plus everywhere, and we'll find that this becomes twice cosine AAB plus ABC plus ACD, da-da-da. Okay. So it's the directed sum of this vector potential around this hexagonal loop, which is actually the lattice curl of A. Okay. Yeah, I don't know how readable that is. The eraser is making everything very white. So let me write it over here again. Oops. and those of us familiar with electromagnetism or remember our freshman physics know that this is the usual definition of the magnetic field. Okay. Okay. Now this looks like kind of a simple model. Admittedly, to really come back to the original model, we need to take the limit u goes to infinity, and we should also remember that there's a constraint, which is that just the original constraint that the total spin on every tetrahedron was 0, and this is just that the divergence of E on every tetrahedron is 0. This is just the constraint. This is just the Gauss's law constraint that there are no charges. So this actually looks kind of simple. What makes it hard, of course, is that one has to take u to infinity. And there's another. It's important to remember that E is half integers. Okay. This is called a compact U1 lattice gauge theory. It's compact because the electric field is discrete, or equivalently, the vector potential actually is a phase. Okay, so it's only defined modulo 2 pi. The electromagnetism you're familiar with from freshman physics, or maybe you quantize it eventually in, I don't know, third-year physics, is non-compact U1 lattice gauge theory, where instead of cosine curl B, you have B squared. Okay. So it's kind of obvious you can get from this to that one by Taylor expanding the cosine. Okay. And that would be valid if k was much bigger than u. Okay. It would be obviously valid if k is much bigger than u in this model. If u is very small, then a is almost a good quantum number, and the cosine is minimized if curl a is small. And so we'd expect small fluctuations. You can expand the cosine. Of course, we're actually in the opposite limit. And indeed, if this was the more standard U1 gauge theory, if you actually look in the textbooks, the commonly studied U1 gauge theory doesn't have this. Okay, doesn't have the half. The textbook lattice U1 gauge theory is the one where E is integers, actually. Okay. That model is actually trivial if you take u to infinity. Because if you take u to infinity and you allow E to be an integer, then it's just minimized when E is 0. This model is still non-trivial when you take u to infinity because you're left with E equals plus or minus a half. It's just the same model we started out with. Okay. Classical, no. Not necessarily. So this model, actually it has the same behavior if it's integers or half integers if k is large. Doesn't matter. Okay.
But I mean, if u is large, then...
Yeah, so if u is large and E is integers, then it's basically trivial. So the ground state is, to a good approximation, just the state where E is 0 everywhere. And that's a product state. Okay, it's a totally non-entangled state. It's not a very interesting state. Okay. On the other hand, if k is large, then we get a more interesting state. Okay. So it turns out, okay, that for this half integer case, which is sometimes called an odd gauge theory, but this word is used in different ways, so I'm not sure I really want to encourage that too much. Actually, there's no phase transition between large u and small u. It's just in the same phase everywhere. Okay. I don't know what I'm trying to graph here, but u over k, 0 everywhere in here. It's all in the same phase. Okay. On the other hand, if it's integers, it actually has a phase transition between this trivial phase at small k and the trivial phase and non-trivial phase at large k. So if you accept that, and really the only way to know that that's true is by studying the original spin model. Luckily, as Roger explained, actually that spin model doesn't have a sign problem in Monte Carlo, and it was studied by Youngbeck Kim's group some number of years ago. I don't remember how many. Indeed, they were able to show by numerics that it's really in the same phase as the small u limit. Okay. So that's a leap of faith. I don't remember who asked me about it, but someone back there was asking.
So they studied the half integer, the other one?
Yeah, they studied the original, so the model at u equals infinity for half integer. Okay, the original spin 1/2 model. They're not the only ones. Also, Nick Shannon's group has studied this ring model more recently. Yeah. So with that assumption, we can get some understanding of this thing by just looking at it at small u or large k. Okay. So we have a leap of faith. Large u is the same qualitatively as small u. If we make that assumption, then it's natural to just say it's OK to expand the cosine, and we end up that the effective Hamiltonian is approximately u times the sum over links of e t prime squared plus k, sum over links t prime. It's not links. Hexagons, b hexagon squared plus a constant. So that should look very familiar. It's just the energy of an electromagnetic field. Okay. So this is just lattice quantum electromagnetism. Okay. So what do we know about lattice quantum electromagnetism? Okay. Well, we can go back to the beginnings of the understanding of electrostatics. Mr. Coulomb discovered the law of interaction of forces between charges. Okay, so we know that electromagnetism gives 1 over r potential between static charges. So we can ask, what are these charges that would experience this 1 over r potential? Note there's a power law here already. Okay, so the fact that we see some kind of power law already tells you something is very different from a topological phase. Okay. What is that? Well, okay, so a charge is just a divergence of E. Okay. So if we have a localized charge, we should have that this divergence is non-zero somewhere. If you remember what this is nothing but up to a sign. The charge on a tetrahedron is epsilon t sum on spins of SI z. Okay. So a localized charge just corresponds to a tetrahedron which has a non-zero total spin. Okay. So remember st equals 0. I'll call this stz. This corresponded to a tetrahedron with 2 up and 2 down spins. Okay. The smallest charge state we could make, which is non-zero, would be stz equals plus or minus 1, which would have, let's say, 3 up and 1 down, or 3 down and 1 up spin. Okay. So that's this is what corresponds to a charge. Okay. And the analogy to electromagnetism tells us that if we have such a charge, there are going to be field lines emanating from that thing. Of our charge, little defect tetrahedron. Somehow there are electric field lines emanating from it, which is what mediates the 1 over r forces. So there would be a 1 over r potential, sorry, not force, between 2 such tetrahedra. Okay, if we make them static. Okay. The fact that this thing has field lines emanating from it actually means that it's not a local object. Imagine we wanted to actually create this quantum state. Okay, you want to create this charge somewhere. Well, the charge is always accompanied, according to Gauss's law, by an electric field pattern around it. So to actually create that quantum state, I can't just act locally and change the charge. I have to also create the field lines around it. Okay. So if I want, to have an operator which acts on the ground state and creates this charge, called an electric charge somewhere, my operator can't be local. It has to actually create that field pattern. Okay. So this is very similar to how an operator that creates an isolated E particle in the toric code has to act along a line of bonds. Okay. Because the E particle also has a string emanating from it. All right. The difference, which comes back to somebody's question earlier, is that in electromagnetism we can measure an electric field. Right? I could do it by putting another test charge somewhere. So it's possible to locally measure that electric field. That's not true for a topological phase. These field lines kind of fluctuate so much that there's no way to detect them locally. Okay. But that's not true for a U1 gauge theory. So that's a way within the gauge theory to see that this effective charge is non-local. How do you think about it in the spin language? Okay. Well, I already told you, it looks very simple. Just a tetrahedron with 3 up and 1 down spin. In particular, why is this non-local? Doesn't look that non-local. Okay. Well, we could try to explicitly construct an operator which creates one. That would be one way to proceed. But in this case, we have one advantage over the toric code, which is that our microscopic model has more symmetries. Okay, if we remember, we had the original model was actually an XXZ model. And this has a nice symmetry. In particular, it has a physical, not gauge, U1 symmetry, which is that the total SZ is conserved. So that means we can label all our states by the total spin SZ. Okay. Actually, we can ask, what's the total spin SZ of this electric charge? Okay. Well, the total spin SZ, it's the sum on all sites of SIZ. Okay. In our new notation, we replace the sites by bonds. We cover every bond like this. So this is, if we cover every bond, we can do it by covering actually, I don't even really need to do this. Let's write it like this. Okay. So we can break up this sum into sums of tetrahedra and sum over the spins on every tetrahedra. But remember, tetrahedras share sites. So every site is part of 2 tetrahedra. So if I actually sum this, I will get twice the total spin. So I should really put a half in here. Crap. So this is 1/2 the sum on tetrahedra STZ. Okay. So if we have a state where only one tetrahedra like this has an integer charge, then this total spin is going to be plus minus a half. All right. Okay. But there are no states where the total spin is plus minus a half. In any finite system, they don't exist. Okay. You start with the ground state and you start flipping spins, you always create integer spin states. Okay. So this can only exist as a non-local excitation. In fact, in any physical system which is finite, they'll always be created in pairs. Okay.
as you can see, they just flip a spin.
Yeah, so that's a more, pictorial argument, very similar to what we did for the toric coat. One can think about flipping a spin. You'll see that you immediately create two of these charged tetrahedra, and you can keep flipping spins to move them far apart. Okay, but here we can do, elementary school algebra. Let's see. Okay. Yeah. Okay, so the original Hamiltonian, just an XXZ model, it conserves SZ. It's invariant under rotations, global rotations around the Z-axis. So that's a physical symmetry. Okay, it's a global symmetry. The original model doesn't have any gauge symmetry. Okay, it's only once we did the degenerate perturbation theory that the effective model has a gauge symmetry, which came about from the fact that in the classical limit, the ground state was obeyed this local constraint. But in the full model, there is no such symmetry. But there is a global SZ conservation symmetry. Okay. So this is a physical quantum number. Yep. No, you can't because the gauge symmetry is U1. But well, that's the standard thing you do when you generate a symmetry from a conserved quantity, right? So it has that symmetry. We're allowed to do that. So therefore, it's a symmetry of that Hamiltonian. Right? So, I didn't introduce any artificial variables or anything when I derived the effective Hamiltonian. I just did perturbation theory. We arrived at this term with the 6-spin interaction. Now we're free to analyze that. We look at it and we ask, what are the symmetries of that Hamiltonian? That Hamiltonian has a local U1 symmetry. Okay, that's the maximum symmetry we could find there, plus some spatial symmetries, some point group symmetries. Okay. Yeah. Okay. What is special, I should say? So anytime there's a model like this where you're adding quantum dynamics to some classical model, and the classical model has a ground state space which obeys some constraint, some local, real valued constraint. In principle, you get a U1 gauge theory out of that. You're guaranteed. What's not guaranteed is that it's a pure gauge theory. So, in this rewriting, we see that all the variables are actually gauge fields. Okay. But there are other gauge theories which have matter fields in them as well. The usual, like electrodynamics, if we put electrons in, we don't just have gauge fields, we also have fields for the electrons. We're not guaranteed that there won't be fields like that appearing. So that is special to the geometry here. There was another question. Yeah, right. So, okay, if you want a picture, maybe I should have drawn the picture. The picture is very similar to toric code. Okay. In our ground state, we have SZ equals 0 everywhere, but let me use this kind of Kagame picture. Highly distorted Kagame. It's topologically equivalent to Kagame. Now, we act with S plus here. Okay, we create a positive gauge charge and a negative gauge charge here. Okay, and now they're nearby, but so now we're actually in a subspace, which is not what we described. Okay, we derived an effective Hamiltonian for the ground state subspace. This is not the ground state subspace anymore. Okay, so if we really want to derive an effective Hamiltonian for these kind of states, we should go back to the derivation. And one should be careful because it was only in the ground state subspace that the lower orders in perturbation theory don't contribute. So in this subspace, actually, first order in perturbation theory can contribute. In particular, we could act with J plus minus on this bond right here, which would actually move this down particle from this tetrahedron to this one. It was you who asked the question, right? Yeah. So actually, if we try to describe now this subspace, which is the ground state subspace plus 2 excitations, we'll see that individual excitations actually can hop. Okay. So they have some dynamics with a bandwidth of order J plus minus. Let's see in the brown shirt back there. Yeah, okay, that's the next thing. Are there other questions that come before or similar? Yeah. Yeah, you don't really create, of course you don't create an eigenstate that way. You create some superposition of things, and it would take some time for the dipole field to develop. Okay. Yeah. Okay, so it's very much like the toric code, which I also didn't talk about that. The toric code has this gauge symmetry built in. Okay, but you can actually add terms to it. You can add, let's say, a magnetic field coupling to sigma x, sigma z that break all those symmetries. But the state is robust to that, and exactly the same thing holds here. You can break any symmetry, and the state is robust. And with these gauge symmetries, there's usually a way in which one can, even with the perturbation, restore the gauge symmetry. So let's imagine, for example, I added, I don't even know what a good thing to do is. I mean, by construction, we actually started with a model which had no gauge symmetry. Okay, XXZ model didn't have it. All right, it was just because we took the procedure of degenerate perturbation theory that we arrived at a model with gauge symmetry. And that will be true to all orders, no matter what we add. Okay, in that sort of approach. Okay, we can try to do something beyond perturbative and try to understand the physics in a larger subspace. And that you can kind of see a hint of it here. This is. Now we have added particles to it, and this is a different subspace. So this is corresponding to adding charges. This is the matter field sector. When you add perturbations that break this gauge symmetry, what you're really doing is adding matter fields to the problem. But when you add small terms that break the gauge symmetry, you're adding matter fields that have a large gap. Yeah, to go into discuss this in any kind of detail, I think would be impossible given the time. Already it's impossible for me to get done what I wanted to get done, but that's all right. We got good questions. Yeah.
So visualization is phase. Electric field.
Yeah, great. Okay. Yeah, so this is a great question. Okay, so let me come back to it, and there was also already the question about the monopole, so I kind of want to get that. So let's first use our intuition for electromagnetism. Okay, so that we learned that there are electric charges. So these are the analog of the E particle in the toric code. They're a kind of emergent elementary excitation of the U1 gauge theory. So in our real world, we don't have magnetic monopoles, but in a compact U1 gauge theory, they actually exist. You could call them M charges or magnetic monopoles. They exist because when we actually derive this gauge theory, the vector potential is actually a periodic variable. So it's only defined modulo 2 pi. As a consequence, there isn't a strict conservation of flux You define flux as the curl of A, and so when you integrate it over a surface, if A was everywhere well defined, we should have that the integral over the surface is the volume integral of the divergence, which is 0. But the divergence itself is only defined up to 2 pi. And it turns out that you get violations of that on the lattice scale, and these correspond to magnetic monopoles. Okay. These are much harder to visualize. Okay. Because they're textures of the dual variable, they're textures of this vector potential. Okay. But they exist. And three-dimensional electromagnetism, 3 plus 1 has electromagnetic duality, so actually electric and magnetic monopoles have the same kind of interaction. The magnetic charges also have 1 over r interaction between them. And the third, bless you, the third, well-known ingredient of electromagnetism is Maxwell's discovery. So we move from Coulomb, I guess we could say this is Dirac, to Maxwell. He discovered that out of electromagnetism comes light. Since it's quantum electromagnetism, we have photons. Okay. So a photon is a wave in vacuum, right? So it doesn't require any charges. So a photon actually, unlike these two things, which are outside of the ground state sector, they're defects in this kind of quantum spin-ice texture. This is something that lives within the ground state, classical ground state manifold of quantum spin-ice. So this is a kind of collective mode. And we should expect that, so I said that this quantum spin liquid, U1 quantum spin liquid is gapless. It's gapless because it has this photon. Okay. So just like light, there'll be a collective mode which is linearly dispersing at small k and has 2 polarizations. Everything is the same as usual electromagnetism. Okay. Good. Okay. And like the toric code, all these features are robust. So any perturbation of the model, as long as it's weak, will preserve these features. There's other similarities to toric code. The toric code has the E and the M particle, and we can combine 2 of them to make an epsilon. That's something that's well discussed in the literature on quantum electromagnetism. You can have a bound state of an electric particle and a magnetic particle, which is called a dion. In this theory, the electric and magnetic particles, they're actually bosons, and this dion, just like the epsilon particle in the toric code, is a fermion. Okay. So like the toric code, 3 dimensions, you have fermions coming out of bosons. Okay.
You're saying that 3 dimensions,
Yes. Yeah.
So in the Pyrochlore, the bulk gap helps us show that it's absolutely stable.
Mm-hmm.
How can we be sure that this is stable to arbitrary perturbation?
You're going to have to trust me. But it's true. It is. So why is it stable? Okay. I kind of alluded to it. So we can imagine adding 2 kinds of perturbations. Of course, they can't be strong. If they're strong, then we could destabilize. Should be weak. Okay. We can add perturbations which preserve the gauge symmetry. Okay. And then, if that's the case, we can express them always in terms of E and B. Okay, those are the gauge invariant variables. Then symmetry will not allow us to write anything down besides E squared and B squared. Okay, so all we can do is modify the, or higher powers, which are irrelevant. All we can do is modify the electromagnetism. The more subtle thing is terms that break the gauge symmetry, since it's not physical. But what I told you already is that terms that break the gauge symmetry can actually be always re-expressed in terms of matter fields that are coupled to the gauge field. And those matter fields, when the perturbation is weak, have a large gap. So it's protected by the gap of the matter fields rather than any property of the photon. A different way of viewing it is a little less physical, but you might like it better, is that there's a well-known result for gauge theories called Elitzer's theorem, okay, that no non-gauge invariant expectation value can can be non-zero. This implies that order by order in perturbation theory, in any non-gauge invariant term, only the gauge invariant combinations survive in perturbation theory, and they can always be re-expressed in terms of E squared and B squared. Okay, so that's how you actually see it coming out if you do just stupid calculations. Yeah, so in some deep sense, but I don't know how to make it rigorous exactly, the deep sense is that everything is protected by, really protected by degenerate perturbation theory. The fact that the theory lives in a certain subspace of the Hilbert space, which is gauge invariant, and that the non-gauge invariant subspace is separated from it. So no matter what perturbation we do, we kind of smoothly move states in that Hilbert space.
But if it just went beyond perturbation,
Yeah, so we can study, you could study other, corrections to other levels. They would still be degenerate, actually, so still degenerate perturbation theory, but not gauge invariant. So that's equivalent to studying, renormalizations of the particles in the theory. You can find out, how does so in the classical model, for example, the energy of a charge is something like JZZ. But it'll change a little bit. It gets corrected by of order J plus minus, et cetera. So you can study those corrections. Yeah. Well, that's not degenerate perturbation theory, though, right? So, the philosophy of perturbation theory is you have a certain set of states which are separated in energy from other states. And in perturbation theory, we follow those states as they evolve with some coupling, okay? And so the degeneracy of that subspace is just always maintained, okay? You can study mixing, okay? That will end up being, that's equivalent to adding matter fields, okay? So we can do that. I mean, actually what Lucille did as part of her thesis work, this was basically formulating the problem that way. So I'm kind of, you should ask her. Yeah. No, okay, so there you can have a confined, so this is so the aficionados of gauge theories will know that they typically can have confined and deconfined phases. Okay, this is known as the Coulomb phase of that gauge theory. So if we take the even gauge theory, so we take E to be integers, and we increase U, it will undergo a confinement transition. Okay. We can also achieve a confinement transition for the odd gauge theory by adding couplings between electric fields at different bonds. Not within that. This model only has one phase, but because it's odd. But it's not obvious, but it's true. Okay. Just that the large U limit is very frustrated. Okay, so we know in the large U limit we can map it back to that spin model. And now one has to study that spin model. So let me give you a physical picture. I think this is helpful. It also gets back to Leo's question, okay? So let me go back to the original model without all this U stuff, okay? It was just a sum over hexagons minus K of this kind of Si plus, Sj minus, Sk plus, da-da-da. All right. So this thing lives. It should be projected into the ground state subspace. So what does this actually do? So we have these various classical ground states. Acting on one classical ground state, it moves you to another classical ground state. Okay. How should we think about the classical ground state? So this picture. No. It's always confusing to me to draw these things. Okay. This picture, in terms of a gauge theory, suggests that we should think in terms of the field lines of the gauge theory. Okay. Field lines just correspond to spin configuration, so it's pretty physical. So we know that in the classical ground state subspace, we always have 2 up and 2 down spins. Okay. So let's imagine we just draw the up spins. Those up spins, there are going to be 2 on every tetrahedra. They look something like this. Okay. There'll be another tetrahedra over here. There'll be another spin. Okay. If we remember that these lie on the links of some lattice, it really shouldn't be a straight line. I don't know why my picture looks like a straight line. We could just color the links associated with these up spins, and we can see that they form closed lines. Those are really the electric field lines, essentially. Okay. In any one of these classical ground states, every tetrahedron will have a line coming in and a line going out. So they never end. They have to form either extended lines or closed loops. And this ground state, can be some kind of, any classical ground state is some sort of complicated loop pattern on the lattice. Okay. What this Hamiltonian does is it acts on some hexagon and either adds or removes some elementary loop. If there's a loop present somewhere in there, it can reconnect it in some ways. So very similar to the kind of pictures Chaitin was drawing for the toric code when he was talking about that. This moves you from one pattern of loops to another. So now we can think about, just try and intuit what would this Hamiltonian like to do. Well, it's a kind of kinetic energy. There are different things that could happen. So one kind of simple thing that could happen is that to get the best energy for this Hamiltonian, we form some superposition of many, many different. We obviously have to form some superposition. One single pattern is going to be very bad here. We can form a superposition of almost all the loop patterns. Okay. Then if we act on one of those loops, with this thing, it'll form some other loop pattern, which is again in the wave function. And so we get a pretty good matrix element. So that's one possibility. So this is, so one possibility is that this Hamiltonian basically delocalizes the system amongst loops. Okay, amongst the whole Hilbert space. Okay, so if that's the case, then our wave function, our ground state wave function, is something like the sum over all these loop patterns of some big mess, with an extensive number of things. That's looking very similar to the ground state of the toric code. In the electromagnetic analogy, this is a system with a lot of fluctuating loops of electric fields. So these are like vacuum fluctuations of the electric field. Okay. And so this is a picture that corresponds to the Coulomb phase. Okay. It's not.
Sometimes you're saying like real.
Yeah. So of course, I chose, when I'm drawing this, I'm choosing to write the state in an SZ basis. So the pictures are in terms of electric field lines. But we could have chosen to write it in a vector potential basis. It would have looked like magnetic field lines. It's not the only possibility. Another possibility that might happen. So what's good about this state is it's kind of a uniform superposition of everything. So every one of these, we have a sum of hexagons. Every one of these hexagons is equally happy. Okay. Another thing we could do is to try and find a compromise. We could pick a set of hexagons and do the best we possibly can for those hexagons. So that's a rather different thing. We could choose a wave function. We could choose a wave function which is like is more like a product state. We have a product over certain hexagons, special hexagons. And on each hexagon we have we kind of resonate that hexagon. So we optimize, find the best state on that hexagon. Okay. We can't do this for every hexagon because those hexagons overlap. Okay. So this will have better energy for some of the terms in this Hamiltonian and terrible energy for others. Okay, so there's kind of competition between these two things. In the magnetism literature, this is kind of what would be called an order by disorder state. Yeah, so this breaks translational symmetry. Other symmetries, you have to pick a set of hexagons. So this could happen. Okay, it happens sometimes in models like this. There's no guarantee. It's only by really, studying this model numerically that we know that this is the case and not the other. Okay. Yeah. Yeah. Okay. Good. So now you're asking about ground state degeneracy. Okay. Yeah, you had to. Okay. Okay, so let's pursue that. Okay, so there's no real ground state degeneracy because it's a gapless system. Okay, but there's something a little bit like a ground state degeneracy. So the ground state degeneracy in the toric code, let's go back. How do we understand that? It corresponds to the option to put a loop of, say, electric flux winding around some direction of the torus. And that loop of electric flux is, that commutes with the Hamiltonian, doesn't cost any energy. It's not really observable by some local measurement. Okay. So a similar thing is here, and we could do magnetic flux. Similar thing we could try to do here. We can, there indeed are states in which you have electric flux that threads some periodic direction of space, or magnetic flux. Both of those things are allowed. But the difference I already mentioned is that electric field lines and magnetic field lines are measurable. Okay. So they spread out, but they because they're U1 quantities, you can kind of measure them locally. So you can ask, what's the lowest energy state with one kind of quanta of electric flux threading the cylinder? The best thing you can do is to spread the electric field out over the plane transverse to your periodic direction. You have a flux of order 1, it spreads out over an area of L squared. That means you get an electric field of order 1 over L squared. The energy of an electric field is the integral of E squared. So E squared is 1 over L to the 4th. You integrate that over L cubed, you get an energy of order 1 over L. So the things that correspond to degenerate states in a topological phase here have energy of order 1 over L. Okay. So they are not that low in energy. Actually, I have to say that's the same scaling of energy as the photon states, which are not topological at all. They're just particles. So there's no real topological degeneracy in a non-topological phase.
Just to be clear on the spectrum, so if you were to draw the many-body spectrum for the large gap, how do you take the gap that would bind?
Oh, much smaller, right? So there's a finite gap, which is some order 1 number, JZZ here, okay. And then there are particles, for example, the photon has a bandwidth of order k. So there's actual band of those particles. And then there are kind of, you would call zero mode excitations, non-dispersive excitations related to background flux, which also have energy of order 1 over L. So there are lots of low-lying excitations well below the mass gap. The monopole gap will be of order k. Yes, that K. Yeah. Not momentum, yeah, large K. I see that I'm not going to do partons at all, and we're already over time, but I'm happy to keep answering questions, sure. Yes. So there's some work on figuring out, how the entanglement entropy scales, for example. It's much trickier than for a topological phase because it's gapless. So there are all sorts of contributions. Even a much more trivial state like an XY antiferromagnet has non-trivial corrections to the entanglement entropy that just come from the Goldstone modes. Here we have a photon, which will also give contributions, and you have these kind of zero mode contributions. So one can study it, but for example, numerically, I don't think there's anything. If Roger were here, maybe he could tell us. Yeah. No, so the global U1 symmetry is unbroken. So the photon is something different. It's not a Goldstone mode. Okay. So in particular, it's robust. So if you have let's say you have a broken symmetry state like a Heisenberg antiferromagnet, it has 2 Goldstone modes. Okay. But if you come in and you break the symmetry, you put a magnetic field on or you add some crystalline anisotropy, it develops a gap. There's no perturbation here, which is weak, that ever opens a gap. Completely robust to that. That's in principle a testable feature. No. Yeah, so that's a feature which is new to this kind of ultra quantum phase that's beyond topological order. Yeah, so just if you want to take that really far, you can say, look, we have now a model. Of course, elementary particle physicists have understood the theory of the fundamental forces up to, but not including gravity. Right? You have a nice standard model that explains everything, but doesn't actually explain where the forces come from. Okay, so this is a stupid model of a rock. It's actually not a bad model of some rock. But in this model, it explains where electromagnetism comes from. Okay, it's a step better than the standard model, at least for electromagnetism. And if you want, you can, and people try, especially like Xiaogan Wen or my colleague Senka Xu have been working on generalizations of this to explain the other fundamental forces. So you could hope that, and you could find a model with which doesn't have any gauge symmetry, but where fundamental forces emerge.
Is it possible that you can get a
Sure. So yeah, there's work studying other possible U1 spin liquids. So including things like that, E dot B term. So long ago we did some work on something called topological mod insulator, which is something like that. More recently, Senthil and Chong Wang have a number of papers exploring different types of time reversal symmetry realizations in U1 spin liquid. There's K. Yeah. When U is small, very similar. Yeah. So if we now we're not in the spin 1/2 picture anymore, but if we just take that compact U1 gauge theory, we can still work in the electric field basis. And when U is small, it's a very large. That means E is a very highly fluctuating variable. There are lots and lots of lines of flux. They're not just the smallest line of flux. In this some sense, in the spin 1/2 case, we only have the minimum possible strength electric field. When we relax U, the field lines can have a larger strength. They can. All right. Sounds good. Yeah, I had a pad over here. Did I carry it over there?
What?
Oh, I wonder what I did with my pad. Are you up next, Steve?
Yeah,
Somebody's going to raise the board for you, so don't.
right. So these waters are available. Good.
Yeah, water is good.
Yeah.